Hello everyone, today I'll be presenting a large-scale robustness analysis of video action recognition models. Our work in summary is benchmarking action recognition models on real-world distribution shifts from either perturbing commonly used benchmark datasets or by curating real-world distribution shift using keyword search to find uncommon variations of an action class. Our evaluation resulted in several findings. These include that when models are pre-trained, they are typically more robust than those trained from scratch. We also found that models are typically very robust to temporal perturbations on most datasets, but when the activity being evaluated has more temporal elements, such as it has an activity that is its reverse, models struggle, even when it's not temporal order that is affected. When comparing architectures between the selected models, we found that typically the transformer-based models were more robust. Finally, when actually training the selected models on corrupted video, we found that the CNN-based approaches improved relatively greater compared to transformer-based approaches. The motivation of this work is to look at how is performance impacted by a natural distribution shift, and this can be from either curated real-world video or from simulated perturbations. Here are some more details about the perturbations we use to generate corrupted video. So on the left, we have the summary of our high-level perturbation categories and the individual perturbations underneath them. And on the right, we have some examples of those, such as freeze from temporal, impulse noise from noise, random rotation from camera rotation, and motion blur from blur. For each perturbation, we also have 5 severities, and these range from 1 to 5. And here's 2 examples where the top one is a temporal perturbation freeze, and in the bottom is an example of motion blur. For the perturbed datasets, we use 4 benchmark datasets that are very commonly used in action recognition. The first we have is UCF 101, which has 101 action classes. Then we have HMDB 51, which uses 51 action classes. We have Kinetics 400 with 400 action classes. And we have something version 2 that has 174 action classes. We call our curated dataset UCF 101 DS for distribution shift. It contains approximately 4,700 clips with 47 action classes from the UCF 101 dataset. On the right here, we have an example where we have a frame from an original video in the dataset for a given class, and then we have a frame from an example video from our distribution shift version of the class. So here we have the class's balance beam where there's a human actor, and on the bottom we have a video frame from our data set where we change the actor to a cat. We also have some video examples here. These are collected by using keyword searches that have both the action class and the distribution shift of interest. We also categorize these keywords that are specific to the distribution shifts into a higher level category for better analysis. So for example, that can be an actor change, and the distribution shift keywords could be bike riding animal or bike riding in a costume and those kinds of things. In order to measure how models are impacted by these distribution shifts, we use 2 different measures. The first is relative robustness, which measures the relative drop in accuracy, and absolute robustness, which measures the absolute drop in accuracy. Both of these metrics compare the accuracy between the clean video and the perturbed video. Now I'll go through our findings. First, I will go through the overall results for the different higher level perturbation categories for all the models. So on the y-axis, we have the mean accuracy for 2 different data sets. On the top, we have kinetics, and on the bottom, we have something version 2, which is a more temporally challenging data set. On the x-axis, we have the different severities ranging from 0, which means clean, and 1, which means the first start of a perturbation, all the way to 5, which is the most severe version of the perturbations. Our models are here indicating the different colors. So we'll start with pixel noise and blur, which are pretty identifiable as humans. However, as you can see, as the severity increases, models really struggle, and that's for both data sets, so it doesn't matter whether they're temporally relevant or not. When we have some more temporally relevant perturbations, such as compression, which is spatiotemporal, and just temporal perturbations, we see that the models struggle a lot more on the something version 2 data set. In this, for example, with compression, there is no reversing or change in the temporal order, and models are still struggling here, while temporal has some modification of the temporal order, so you see a greater struggle there. Both models seem to struggle as severity increases with camera, but more so with a more temporally challenging data set. Now I'm going to talk about how pre-training impacts robustness. So here we're comparing models that are trained from scratch on the target dataset to those pre-trained on Kinetics 400 and then fine-tuned on the target dataset. These visualizations show the different categories of the perturbations and the different model performance. The closer the lines are to the outer circle, the higher performing. As you can see when comparing the models from scratch to pre-trained, in some of the categories you see some noticeable increases in performance when they're pre-trained. Therefore, pre-training can generally improve robustness. Now we'll talk about our temporal-based evaluation. Here we're comparing the more temporally challenging SSV2 dataset with the kinetics dataset, with the y-axis being accuracy, the x-axis being the different perturbations averaged across severity. And as you can see, models struggle more on the SSV2 dataset for all the categories. When looking specifically at reversal, we have different action classes that in reverse have another action class. So for example, unfolding something's opposite is folding something. And we're comparing different architectures here where timesformer is a transformer based and slow fast is a CNN based. These are the latent space for these embeddings on the clean data set where there's no change in the videos. And here is when the frames are in reverse order. And as you can see, the timesformer still clusters these feature embeddings into those nice clusters, even though they might be categorizing the action classes incorrectly. So it is likely they're categorizing them as the opposite class. Here in slow fast, we see that the model just gets really confused and is unable to maintain those clusters. Next, we look at training on corruption. So this is where we're taking these models and actually training them on corrupted video. So here we're comparing a CNS-based approach, ResNet 50, and a transformer-based approach, MVIT. On the y-axis, we have the different perturbations these models were trained on. So in this case, we have spatial perturbations only and temporal perturbations only. And then on the x-axis, we have the different perturbation categories with their average here. So when training on the corruptions, we see that performance even helps on the clean data set. So just by training on that, we see an improvement when compared to model performance on clean for both models. When looking at the impact of training on one perturbation category to the other, we see that the CNN-based approach generally increases for both, while here we see some mixed results where the performance gains are not as high. And this is a transformer-based approach, while this is the CNN-based approach. So as we can see, it helps more on the CNN-based architecture compared to the transformer-based. We also evaluated models on our real-world curated dataset, the UCF 101DS. So here's some examples of what those videos look like again. And we found that certain architectures are more robust to these changes. Again, we see the transformer-based approach has higher performance across all the different distribution shift categories compared to our CNN-based approaches here. Thank you for your time, and please feel free to check out our paper and our website.